Okay. So I'd like to thank the organizers for giving me the opportunity to come here to this meeting. And to Poland, this is my first time, and it was one of my dreams to come here, so I'm very happy. Well, actually, this talk is not exactly only about quantum information, but, well, we always end up in quantum information. And also, this is a kind of joint work between theory and experiment. It's part of Nicolas Faber's PhD thesis work. Now he's a postdoc in Warsaw. So he's part of the theory team together with myself and Anne Keller and others here. And the experiment that inspires us a lot is developed in Sarah Ducci's team, who's also in our team, but, well, with some complicated French stuff. So let's start with, oh, it's not working now. Because maybe that's it, yes. Yes, it takes time. So all the fun is good.
Too far.
Okay, so it's not working, but it's not. I mean, oh, it is. Okay, I think it will be complicated, but let's see. So we're going to talk about, well, frequency is one of many of photons, of the properties that photons can have. We're going to talk about this today, and about the relation between these properties and photon statistics and intensities of different photon states. So we know some of photonic properties, so let's start with the fun part. We know very well polarization. That's a discrete degree of freedom that is usually associated to qubits and is used in quantum information and to test non-local properties, for instance, on non-classical properties of light. We also can talk about orbital angular momentum or different modes that are used as qubits as well, or as quantum channels. And of continuous variables as well. Today we'll be mainly interested in frequency, but the results will apply to other different degrees of freedom that are continuous in photons. So when you put many photons together, so do these different properties, and so there is a kind of confusion mixing up between these properties and photonic statistics. They should be separated. So this is why we're considering here a kind of simple scenario in order to compare things, which is the situation where either we have many photons in one or in different, very well-defined modes, or we have one photon that has many different modes, as, for instance, different colors. So actually, the meaning of the word mode here, is not exactly the same, I guess. But, well, this is the same that we can discuss later. So, well, this X1 to N are different properties that a photon may have, but if they're all the same mode, they share the same properties, let's suppose it like this. And this is the situation where a single mode or different modes have many photons. And usually, we can define these continuous variables, which are X and P. And if we talk about continuous variables, what's important here are photon statistics, and mainly non-Gaussian aspects are very important for non-classical physics and computation. And this is something that can be seen, for instance, using phase-space distributions as the Wigner function that's here. So I have a Schrödinger cat and a kind of exquisite state. So experimentally, I have many ways to encode these continuous variables as vibrational motion of trapped ions. We're not going to talk about this today. And the quadratures of different modes of the radiation field. And people got interested on this kind of setup because they can be deterministically generated. And they can be measured with very high efficiency. For instance, using homodyne detection that has been mentioned many times today. It's sometimes hard to isolate modes, and actually preparing these relevant states, which are non-Gaussian states, is very difficult because it involves photon detection, and then determinacy is lost, and so we're always limited in the number of non-Gaussian states that can be realized in practice. So something that is very useful whenever we talk about continuous variables is kind of borrowing this vocabulary from quantum information. that involves defining this universal set of gates, which are a finite number of operations that combined enabled us approaching evolutions that are arbitrary polynomials in X and P. So this is something that also happens for discrete variables. We have this finite number of gates. And then we have something that's more or less equivalent in continuous variables. You have these displacements in phase space, this Fourier transform that's analogous to the Hadamard gate that appears there. And you have this operation that's going to be very important today. Here, it's an entangling operation between different modes. And this is the non-Gaussian operator that, appears in this set of gates, but you can have other ones. So if you know how to do these things here, you can do pretty much almost everything. So, so in practice, what you want to do quantum stuff and quantum information with continuous variables, situations as this one, where you have different modes, different colors, and each one of them, you have a different state, a classical, non-classical states, and different statistics. And we're going to compare this as to the situation where we have a single photon in a single mode, but this single mode can be decomposed in different other modes, which are these different B operators that appear here. And the way to mix and these modes together is very well explained in this recent publication of Nicolas Treps and Claude Fabre. And usually in quantum optics, what happens is that we have some nonlinear process that creates a mass that mixes photons and properties here of light and color. And then you use linear devices in order to disentangle this whole thing and create this well-organized states where modes are separated. So how does this organization work? I'll start with a very simple example to see how this can help us understanding the states that are produced in the beam splitter or beam splitter-like device. We have two modes here that can be entangled, is omega A and omega B. For instance, prepared in this entangled state, these are eigenstates of the momentum of one quadrature, for instance. And then after the beam splitter, these two modes, they combine. And what's interesting about quantum optics is that you have this double linearity in the sense that modes combine the same ways as field operators combine, so that you have different modes. And then the state inside the cats change in the same way as modes changed. So if we define these collective variables here, we can see very easily that we can diagonalize the state, put it in a separable form if using a beam splitter. And this is what people do in general. So let's move to a more specific example. Here we have a typical Hamiltonian of a nonlinear device that creates photons at different frequencies, omega prime and omega. And I have this matrix here that has several symmetries, but well, we're not going to use it exactly specifically now. And then what happens is that if this Hamiltonian acts in vacuum, then you create something that's very complicated, that is very entangled, it's an entangled state of different colors. So these balls, these blue balls, they are squeezed states, and these connections between them means that there is entanglement between different modes. This, we can do something that's like the Schmidt decomposition, and then rewrite this Hamiltonian defining different modes and simplify it. So it's a sum of independent modes. It's another way to look at this. It's a kind of a change of basis, exactly as the beam splitter or something analogous does. And then what you have is that another way to look at this squeezed state is kind of a product of different independent modes. So you can relate squeezing to multimode entanglement. And this is something that is done experimentally in many groups where they create thousands of such entangled modes as the ones that are listed here. So now we're going to change systems and move to the single photon regime. So this is a picture of the device that is used in Saraducci's team. I'm not going to describe this in details because, well, I'm not an experimentalist, but and we don't have time. So the main idea is that one photon that enters here is transformed into two photons that we call signal and idler, and they have this comb structure, so they can have different colors. And what we do is that we make a joint detection of these signal and idler photons. We detect the probability of detecting both of them. And this is what we call the joint spectral intensity. And For this setup, this joint spectral intensity looks like this. Well, there are other setups that produce different joint spectral intensities. So we have this diagonal peak structure here. Okay, the Hamiltonian is pretty much the same as the previous one. The point that now here, well, we're in the single photon regime, so that evolution of Hamiltonian should be expanded, and we're using only the first term that creates this photon pair here in the vacuum, these two creation operations. And then if you do this Schmidt-like decomposition, you end up with something which is an entangled state of different modes, this different phi and psi k states. There are different modes. And if it's lambda k, if you have many lambda k, so this is an entangled state that is described using a finite set of modes. So I like to say poetically that photons carry modes instead of modes carrying states. I know we cannot understand this, it's just poetry, physical poetry. So again, the same Hamiltonian. And the point here is that, well, here frequency is not exactly used as continuous variable, as the p's were used as continuous variables before. I'll tell you why. But while here, first of all, we're discretizing this in a set of modes as Q did. And then we were not allowed to implement, we create superpositions of different modes, but independently for each photon here. And this is not exactly the same situation that we had previously. So in the previous case, we combined the quadratules of the field. We had operations that would be equivalent here to summing two frequencies and obtaining, instead of a superposition, obtaining the sum of two frequencies as in a beam splitter. So combining modes, as we do here with beam splitters, works very well for polarization. But if you want to transform frequency in a continuous variables as momentum and position are, this is not exactly the same kind of operation that will enable this kind of correspondence. So let's try to be more clear about what I want to do. If I will compare the two worlds, the world of momentum and position with the world of a single photon and frequency. And then, so these are the cats that appear in each one of them and the states. And then let's try to define these universal operations, what it would look like. So for displacement operations that displaces momentum in phase space, we can define this D, and it would look like this kind of integral that destroys one photon here and creates with a displaced frequency. That can be written in the single photon regime as the same thing as this usual evolution operator of the field. And this T operator here, what's just a mathematical construction in this case, can be obtained by making the Fourier transform of the frequency operator, basically. And this Fourier transform can be written as exactly an analogous way to position and momentum operators. So let's move to this entangling operator operation that is different from that we want to construct in the single photon regime. Well, I can build some mathematical object like this. What I want to do is that I want as input two different frequencies, and then as an output something that is looks like what happened with the position with the momentum operators, like transforming this into sums and differences. And this is something that can be done by this operator here. But this story, well, it's a little bit boring. I'm just writing equations here. Why is it useful for? I mean, and it's unrealistic. Well, to see how this can help us to at least have some fun with quantum optics, let's go back to physics and to this joint spectral intensity. And so what we want to analyze using these new operations that we defined, this state that goes out of this source, of this box, that is used in experiments. So it's this function here that is interested us. And to do this, I would like to talk a little bit about combs and why they can be interesting, because we have this kind of frequency comb. There are many applications, but well, I'll focus on this one. So Gottesman, Kitaev, and Praskil defined what we call JKP states, which are ways to encode qubits in continuous variables that are robust to displacements in phase space. So to do this, they defined these infinite superpositions of infinitely localized squeezed states. And they have these periodic structures, and they're shifted one with respect to the other. And it turns now out that in this basis, in the subspace of these two states, we can define the analogous to Pauli-like operations using displacement operations of fixed distances. So we can also define something that we call stabilizers. I'm not entering into the details, but there are observables that when operators that when measured, we can correct for the errors that would occur in this so defined qubits. So of course, these infinitely squeezed states, they do not exist. So they can also define what we call as physical JKP states that are broadened with respect to the original ones. And this broadening can be seen as errors that occurred, this displacement that occurred with some Gaussian envelope, both in position and momentum. And this kind of states is really interesting and important in quantum information with continuous variables, because if we have, for instance, this kind of what we call cluster states of squeezed states, then it has been shown not only that these JKP states can correct for errors that occur in this kind of state, and also they can be used as a non-Gaussian resource and then enable universal quantum computation in this kind of construction in the measurement basis scheme. So the measurement basis quantum computation scheme consists of, well, you have some complicated states, and then you measure some parts of this and adapt the remaining part in a way that it implements some kind of algorithm or something like this. So it can be shown to be the equivalent to this circuit model, where we implement gates one after another. So we have this problem, which is we have these two photon states of frequencies. Can this be seen as a JKP or not? Well, actually, this slide is just an excuse to put this painting here that I like a lot. And I think it tells a lot about physics as well. So let's try to see. Oh, so the idea would be to define this JKP states in frequency, which is, again, the same thing, an infinite sum or infinitely localized in frequency states. Just a small detail, we can also define the sums of these qubits like changing bases, like an X basis in the JKP basis. And then you can also define these physical states, which again are we have this distribution of displacements in time and in frequency that creates something that is real. So why is this interesting or relevant? Because if you do this and we analyze the state that has this shape, we obtain that actually this state can be written in this complicated form, but that starts with JKP states in frequency. So you have some JKP in frequency, and then do all these crazy operations here, and then you end up with a state that is produced actually by the source. Let's try to gain some intuition about this complicated state. Well, the first part, the first part is this kind of products of JKP states, which is nothing but the products of two combs. Let's try to imagine that these dots, they are infinitely squeezed and localized. It's not the case, I know. But then the distribution of errors, they fatten a little bit in frequency these states. And then this final part squeezes in a diagonal way the distribution. So it's not over. I'm sorry, there's another way to look at this still. And well, for this, we need to, we can easily show that this plus states in the omega base is equivalent to a zero states in the time representation. And then, well, this first part would be equivalent to two qubits that enter in a circuit, and then they are subjected to some displacement errors, which is independently act in the qubits. And then you have this strange part here that involves sums of difference of time. And in order to understand this, let's recall this kind of beam splitter-like operation that we had defined previously. And then we can show that this displacements in collective variables, they are equivalent to this small circuit here, where we entangle qubits and then displace them, and then we disentangle. So why is this interesting? Well, this is interesting, but it has been shown by Nicolas Fabre in his PhD thesis and in this PRA that appeared in 2020, that this can be used as well as a resource for this famous measurement-based quantum computing. So that if you measure one of the photons, say the signal, then and you use this information to act and correct the idler, then this is a small cluster for measurement-based quantum computing. So it can be, it enables error correction perspectives to create more complex entangled states using nonlinear systems with single photons, with with entangled photons. So we have talked about one part of continuous variables with single photons. Now we haven't mentioned phase space yet. And for this, I talk not about the Hongo-Mondo yet, but about the U-Mondo experiment that I think it dates back to the 80s. I'm sorry, I didn't put the references. But it's more or less as the Hongo-Mondo experiment. But at the end, after the beam splitter, they filter the photons at the given frequencies, specific frequencies, each one of them, so different frequencies for the two outputs of the beam splitter, and they detect incoincidence. And what they see is this kind of fringes here. And then, well, if you have seen something that looks like this today, which is the Schrödinger cat, if you look it from the top, actually, it looks like this. And if you cut the phase space, you'll observe as well this fringe structure. And again, this is an excuse to put this painting. And wow, so does it mean that this is a Schrödinger cat or something related to a Schrödinger cat or not? So some years ago, we have worked on the Hongo-Mondo effect. And if you suppose something that is not necessary, but I will suppose this for simplifying reasons, that you have this factorized plus and minus frequency state, actually, you can see that the probability of joint detection can be expressed like this. This is very easy. And actually, this is this W omega minus is the Wigner function in the omega minus variable. It's a cut for the frequency omega minus equal to 0. Okay. So actually, we could imagine. We could imagine adapting the Hongo-Mondo and putting a kind of frequency displacement on it as well. And then, if we did so with coincidence detections, we could reconstruct the whole Wigner function of the two photon state, these collective variables. So we have used this with Sarah Ducci's team in this paper that was published in 2020 to show the difference between two JKP states that were produced by her source. So this is exactly what we would expect for a cut in phase space for a JKP state. And well, this is a kind of displacement that we have realized in this JKP state. It's a logical gate that we have implemented as well. There's very low visibility, but shows the displacement. So, now on the side of perspective, there is this is some ongoing work. Why this phase space-like picture can be interesting or help us on something? Well, on the side of metrology, for instance, some years ago, there are some results that relate some metrology interest of some non-classical states to their phase space structures. So for instance, if you have negative points and you have these fringes, this can be used to detect displacements with very high precision. And recently, there are some experiments that show as well that states that are more or less as the U-Mondo states that I have showed before, like Schrödinger kittens of frequency, they can be also used for this Hongo-Mondo interferometry. And well, the authors observed this kind of fringes And they show that from this kind of detection efficiency, joint detection profile, that the states, they are used for metrology. So of course, the idea is to compare this and say that this is kind of part of the phase space structure of a Schrödinger cat-like state. Okay. So using this kind of states in metrology is something that presents a little bit of issues that we're trying to understand now, which are, for instance, what kind of resource one should consider and what is the classical reference when you talk about using frequency in metrology to display, for instance, time measurements, to make time precision measurements. So I hope to have shown that it can be interesting that to well formalize the relations between one photon in many modes and one mode that's populated by many photons. These two systems, they can be seen as analogous, and it could be interesting to explore other continuous variables, quantum continuous variables that already exist in the realm of quadratures or position and momentum, and translate them into the single photon regime. So thank you very much.
Thank you very much. Are there any questions?
Sorry, when you do the Fourier transform to get this A of t, you have to integrate over negative frequencies in order to do the same as position and momentum. How do you treat that? How do you interpret that?
Yes, well, actually, yes, there are many ways. When you do this in this photon, we can treat this as a difference of frequencies.
Okay.
And yes.
So you shift.
Yes, yes.
Okay.
This is one way to do, but well, let's actually discuss about this, different ways of looking at this, and one of them is translated directly to position momentum, that finally it's more or less the same thing, but yes.
Right.
Thank you. Other questions?
My question is, when you were stating this simple example of entanglement, the mixed state, could you go back to the slide? Could you go back to the slide with this simple example of entanglement with the pinch jitter?
With peace, you mean?
So it's,
yes.
I think it is. Yeah. My question is, what is the difference between the first and second term? Because it's like the difference is PA plus PP, PB, and PB plus PA, for example.
I don't understand.
In the lowest, yeah, here.
What?
Well, the difference between the first and the second term, it's PA plus PB plus. And so what?
There's a minus here. One is one minus.
Yes,
the other.
but I mean the first terms. Why are they?
Oh, they're not different.
They're not different. Okay.
Oh, yeah. Yes, because when you sum, the sum of A plus B is equal to plus B plus 1. Plus A, sorry.
So I just was wondering, because in optics, usually the most destroying thing are photon losses. Yes. So if you talk about this comparison between many photons in single mode and single photon in many modes, somehow the single photon in many modes seems to be very susceptible to loss. So is it really practical to go into this direction, to like increase the complexity of the structure but still keep a single photon, since we cannot protect against losses then, yes? While in other case, we can somehow protect against loss.
Yeah,
so.
Well, there's two things I can answer about this. One of them is that usually when you do this single photon stuff in optics, it's always conditioned to detection. So if you detect it, well, you detect it, so it's not lost. This is one way to do, to say, I mean, yes. And the other is that, okay, I agree, but again, this intense fields, in order to do something interesting with them, you also need to detect single photons, and you're kind of susceptible to this kind of single photon, something that would happen to your state. So at the end, I mean, I don't know how to quantitatively compare these two things, But and third answer is that I'm sorry to say this, but I'm not a very practical person, so.
I was thinking particularly about sensing examples with the structures, sub-Heisenberg structures. And so on.
Yes. But well, again, this experiment that was performed using the Hongo model. Well, the Hongo model occurs if you detecting coincidence, so the photons were not lost. Yeah.
Maybe we still have time for questions. So.
Hi, thanks for a nice talk. I wanted to ask. So it's not clear to me now if I want to have like two systems, which I would call two modes in the original picture, to interact. Can you do this? Because this state now lives in an infinite bandwidth, right? Because now, if I want this single system, effective single system, to interact with something else, can you do it? Like you need to have different time pulses, or what?
You mean to make one frequency interact with the other?
No. So I understand that. Now you're using all the frequencies as a basis for a single system, essentially.
Yeah.
So what about multiple systems? So if I want to have now a beam splitter, logically speaking, between two copies of your system that lives in frequency.
Well, have different photons.
I guess like an analogy of a multi-qubit.
Yeah, exactly. It's the same thing. You have different photons as in polarization. If you have, I don't know, to test Bell inequalities, you have two photons.
Okay.
If can have three to test JZ inequalities and things like this.
Okay. And you can make them interact with this.
Well, you actually, if you're talking, I mean, I think the most interesting way to look at this is exactly in the MBQC spirit, in the sense that using the fact that they have interacted in the past. Because, of course, making photons interact, well, you know that it's not easy, but they have a common origin. And this is more or less the same thing as it's done in the case of MBQC, of this complex cluster states, is that you have some nonlinear thing that entangles them, and then you measure wisely, and then you manipulate your state. The idea, in my opinion, the most interesting one, is to start with something that already happens in nature or in something that's easily engineered, but previously, and then use it afterwards.
Thanks.
Any further questions from the room or online? I think these are old ones that we've not done there. I think we still have
okay, thank
a few
you.
minutes. May I ask the last question?
Oh, yes, of course.
So you used the kind of analogy of the GKP states to bring the multidimensional frequency degree of freedom into just a qubit, a two-dimensional system. Could you think of doing some similar trick like that to make a multidimensional, like a qubit or a q-quartz in frequency?
Oh, yes, of course. Yes, of course. Well, actually, there is another way to look at this column that appears in the GSI. Actually, in Saraducci's team, they look at this as qubits as well. So, so this is another way to yes.
Because the obvious thing is to just do frequency bins, yes?
Yes.
But then maybe there are smarter ways to...
Yes, of course, you can do many things. But what's this JKP, in some sense, it's the idea, it's built to be, as error correcting codes, redundant. So this is why it's kind of a big thing to define a two-dimensional system. And of course, you can define a higher dimensional system, but then you lose this redundancy that's important for error correction. Yes. Yes.
Okay.
Okay.
Thank you. Let's thank the speaker again.
Thank you.